Okay, hello again. Here we go with lesson 9, which is again about shapes, and but this time around we'll talk about water, uh, which has different shape to ammonia that we discussed earlier. Again, as before, let's see what I'm doing right now that I did not do for nitrogen in ammonia. It would be very similar. Of course, the picture would be different, the shapes would be different, but the procedure and the application of your knowledge is similar. So first, like we said before, we have to write the electronic configuration of our good friend oxygen with atomic number 8. Therefore, it's 1s2, 2s2, 2px2. Here, it is important to write the p orbitals in the x, y, and z axes, just to say that. Just to see very clearly that in the p orbital, in the second shell, we have 2 lone pairs. So do you remember what we said? So after electronic configuration, then we have to write, well, actually we established that there are 2 lone pairs. And now let's start constructing our good friend water with, say, hydrogen over there. Again, these are bonding pairs, as we discussed before, but our good friend oxygen has 2 lone pairs, one there and one there. Now, something that we see here that we did not see, the kind of repulsion I'm talking about, we see here that we did not see with ammonia is that since there are 2 lone pairs, therefore we've got a very strong lone pair repulsions. These guys repel the most intense electron charges, negative charges, right? So they tend to repel each other. It's like 2 very strong north pole of bar magnets that repel each other, the strongest. So first of all, they repel each other as much as it is possible, but then each of these lone pairs repel these bonding pairs as well as, of course, do these bonding pairs repel each other. Right? So obviously there is a highly intense repulsion. So you have 1 lone pair repulsion. If in exams you want to write abbreviated letters, you have to write what you understand by LP, what you mean by LP rather, and then you can use it in abbreviated form. So you have 1 lone pair repulsion, you have 2 lone pair bonding pair repulsions, and then you have 1 bonding pair repulsion. Okay, so as a consequence, you can see that the forces of repulsion from the top is enormously more, much more, of a much greater magnitude than the forces from the other side. And therefore, imagine your water molecule is like that, but then imagine the lone pairs are there, and then it pushes these bonds down, and then they come to some kind of agreement, some kind of equilibrium. And at that point, the bond angle here, hydrogen, oxygen, hydrogen bond angle, is, let's put this very clear. In liquid form, water has kinetic energy. And because it's got kinetic energy, it means it vibrates, it moves. So what's the bond angle now? What is it now? What is it now? What is it now? So obviously they take a bond angle, average of bond angle when bond angle is there or here. So the the average bond angle will be 104.5. If you wrote 104 or 105, you would also be correct because it's 105, it's 104. But remember, just to be pedantic, in ice or in any solid structures, the kinetic movement is literally not there. So to be correct, when they say what's the bond angle of ice, in the water in ice, you really have to write 104.5. Even though if you do write 104 or 105, they still don't penalize you. That is my understanding. So the bond angle is that. So now that we've dealt with the 2 lone pairs, so we talked about repulsions as well, yeah? And then now we talked about bond angle, which in this case we discussed. And then the shape is it's non linear, and V-shaped. So all water molecules, which basically comprises about 70-80% of our body mass, are all V-shaped molecules. And of course, the other things that we need to talk about water later on is in intermolecular forces, is how it forms hydrogen bonds, etc., etc., and why its boiling point is what it is, that it shouldn't be. So that's another anomaly. But more importantly, you see how the electronic configuration is helping us to establish and to learn about other things about molecules, shapes, all based on writing electronic configuration, establishing if there are any lone pairs, 1, 2, none, and then decide, right? To cut the long story short, I think it would also be important to mention that our good friend methane, for example, or any hydrocarbons, saturated hydrocarbons, such as our good friend methane, for example, methane itself, well, carbon does not have any lone pair at all. I mean, if electronic configuration of carbon is, well, it's got carbon 6, so you write 1s2, 2s2, 2p2, do you? Well, it certainly isn't that, because one of the 2s electrons migrates into the 2p, yeah, and therefore the whole thing becomes 2s1 and 2p3. And this is when you have the s as well as the p orbitals mixing up. As a consequence of 1s and 3p orbitals mixing up, we have sp3, what is known as sp3 hybridization, which is not, incidentally, in your syllabus, is slightly more degree level stuff, right? So the shape of the orbitals that are formed, well, they don't look like S nor P. S is spherical, remember, and P are double-shaped figure of 8. And when an S orbital and 3p orbitals mix up, they form 4 orbitals that are referred to as sp3 orbitals, and these are it, you know, and they look like something like that. And when you draw them in 3D, they look like that. Now, obviously, there are therefore no lone pairs on carbon. So the only forces of repulsion in methane are bonding pair repulsions. And when 4 bonds repel each other in space, in equally, why shouldn't they? They all are carbon-hydrogen bonds. Why should 2 of them come closer to each other and the other two further away from each other? No. All of them will be pushing and repelling each other away from one another as much as they can. And as a consequence of that, the shape becomes tetrahedral. And the bond angle here is 109. Maybe there is a pattern here. When there is no lone pair at all, and 4 bonds, you have 109. In ammonia, it was 107, wasn't it? 2 degrees tighter, because there was 1 lone pair and 3 bonds. And then in water, it's 105, again, 2 degrees tighter, only 2 bonds and 2 lone pairs. So remembering these numbers perhaps is not as difficult as perhaps you thought it might be. But just remember, of course, there are other things, like carbon dioxide, for example, is 180 degrees. And then we move on to complex ions later on in the course, where we come across trigonal bipyramidal, octahedral structure, all those stuff that are very, very interesting indeed. But then we will discuss those in as and when we come to complex ions. But otherwise, I think that would do for shapes, 2 lessons, yeah? If you learn ammonia, water, and so if somebody out of the blue says, what is the shape of H2S, you must not freeze, because sulfur is in the next group as oxygen, and if oxygen has 2 lone pairs, sulfur has 2 lone pairs as well, and its shape would be the same. If somebody asks you SCl2, well, Cl2 is exactly the same as water. Do you understand? Sulfur 2 lone pair, and the idea of repulsion and lone pairs is exactly the same as before. I think that would do for the time being regarding shapes, and I hope it's been useful. All right, thank you very much. Bye-bye.